Okay, so we are in Unit 3. We're at the bottom of page 9, starting on number 17. So when an object is dropped in the absence of air resistance, it accelerates uniformly. Accelerates uniformly until it lands. However, air resistance is a reality, and air resistance varies directly with velocity. So in fact, the object doesn't keep accelerating. It reaches a terminal velocity. Terminal velocity. This is a velocity that cannot be exceeded. So explain with diagrams why this happens. So we have a dropped object with a mass of 80 kilograms. What does that mean for its weight? Remember, weight is mass times the acceleration of gravity. So 80 times 10, the weight here is 80 newtons. So, 800. So here is my, not quite so much. Here's my 800 Newton downward force. So the downward force, the weight is 800 Newtons at this point. Air resistance initially is going to be 0. And what is the net force? 800 Newtons down. So what's the acceleration? The net force divided by the mass. So our acceleration here is 10 meters per second squared, just like usual. But as we continue to fall, so here we have the weight of the object is still 800, but we have, let's say the air resistance is contributing 100 newtons at this point. So what's the downward force or the weight of the object? Still 800 newtons. Only instead this time the air resistance is 100 newtons. And so the net force here is 700 newtons down. So 800, the 100 is acting in the opposite direction, so they're going to subtract from each other. 800 minus 100 gets us to 700 newtons down. The air resistance is changing our acceleration. So net force is now 700. The mass of the object is still 80 kilograms. I'll fix that on the top one too. Here. Kilograms. There we go. And so now, factoring in the air resistance, our acceleration is smaller. It's only 8.75 meters per second squared. So it continues to fall. Its downward force, its weight is still 800. And at this point here, let's say that the air resistance is 500 newtons. So our weight, 800, our air resistance, 500 newtons, and our net force, 800 minus 500. Net force is 300 newtons down. So the acceleration now, 300 newtons divided by 80 kilograms, we have 3.75 meters per second squared. So the acceleration is decreasing because there is an upward force from the air itself. Eventually, we reach a point. Here's my 800 newtons down. Here's 800 newtons of air resistance pushing in the opposite direction. So the downward force or the weight is still the same, 800 newtons. Now the air resistance is 800 newtons. What is the net force? You have two forces acting in the opposite directions. 800 minus 800, 0 newtons. No force, no net force, no direction. The acceleration is the net force divided by the mass. 0 newtons, 80 kilograms. The acceleration is 0 meters per second squared. What does this mean? Acceleration is 0 meters per second squared. Acceleration is 0, that means velocity is constant, uniform motion. A student of mass 60 kilograms stands on a set. A student of mass 60 kilograms stands on a set of bathroom scales in an elevator. Find the reading on the scales in newtons when we're looking at 4 different situations here. So the first one, the elevator is at rest on the first floor. So at rest, we're talking about no net force. We're going to draw a picture for each one of these. So here is the floor of the elevator. Here's the bathroom scale. Here's the student. So the scale reading would look something like mass 60 kilograms. That means the weight is 600. 600 newtons. And that means that the floor and the scale is contributing 600 newtons to keep the student from falling through the floor. So in order to hold the student up, the floor or the bathroom scale is exerting 600 newtons in the opposite direction. So there's my weight, 600 newtons, and scales read 600 newtons. Then we move to situation B. So same student, same bathroom scale. The weight of the student is still 600 newtons. But there's an acceleration. So we need to figure out what is going on, what's the net force. So we know the acceleration and we know the mass. What is the net force? The student's mass is 60 kilograms. The acceleration is 2 meters per second squared, which tells us that the net force is 120 newtons. Remember, it's a vector, and this is 120 newtons up because the acceleration is up. And so the net force is 120, which means that the force upward is 120 newtons greater than this one. And so we get 720 newtons up. We'll label this as the force up. Force up is 720 newtons. So what does the scale read? The Scale reads 720 newtons. In situation C, the elevator moves upward uniformly at 8 meters per second. So here's my elevator floor, here's the bathroom scale, here's the student. So the weight of this student is still 600 newtons. We'll figure out the net force. So the mass of the student is 60 kilograms. 60 kilograms. And what is the acceleration? Well, it's moving upward uniformly. It's in uniform motion, which means the acceleration is 0. Acceleration is 0 meters per second squared, which means the net force equals 0. No net force. That means the floor of this elevator is exerting the same amount of force on this person as the person is exerting on the elevator, 600 newtons. So in this situation, the scales read 600 newtons. The elevator decelerates at a rate of 3 meters per second squared as it reaches the top floor. Elevator floor, scale, student. So first, we need to figure out the net force. So the net force, we know the mass is 60 kilograms. We know the acceleration is 3 meters per second squared, which means that the net force is 180 newtons. What is the direction? So the deceleration would really be, so if it's going up, deceleration is a negative acceleration, which means that the force, the net force is 180 newtons down. So let's draw a diagram. There's my weight, 600 newtons. Here's my upward force, which is 600 minus 180, 420 newtons. And the scale is reading 420 newtons. Now, if you think about this, you probably actually encountered this in your life. You just didn't have a scale with you, most likely. In situation A, when you're standing on the floor of the elevator and it's not moving, it feels just like you're standing on any other floor. But when the elevator starts to take off and go upward, the upward force is greater than the downward force, and you can feel this as you go up. Your knees kind of maybe buckle a little bit. You feel a little bit heavier as the elevator starts to go up. Scales read 720 newtons. Seems like you're heavier for a second. Then it reaches a constant speed, uniform motion, no net force. Feels just like you're standing on a regular floor. You don't feel heavier, you don't feel lighter. But in situation D, when you are coming to a stop, so you're going up and you come to a stop and it kind of feels like maybe you're floating up a little bit, you feel a little bit lighter, maybe some butterflies in your stomach. That's because of this.